Right, hello again and welcome to the next video on waves. What we've done before is look at what waves are, some definitions of them, then we've looked at doing equations for them. Now what we're going to continue on with is the next part of the topic, and this is something you should be a little bit familiar with, but we've thrown in a little bit more detail now because it's National 5. And so what we're going to be looking at is the ideas of reflection and refraction, right? So let's get started on reflection then. When you think of reflection, you're probably thinking of things like this, okay? You're thinking of trees reflected in the loch, yourself looking in the mirror, but there's a lot more to it. We wouldn't be able to see anything at all were it not for reflection. So in this example that's just popped up here, the light is coming from the lamp and it's hitting these birds, it's bouncing off them, it's reflecting off them, and it's heading back to this child's eye. And he can only see those birds because the light is reflecting off them. So if something doesn't reflect any light, you can't see it. And the light it reflects also influences what colour something seems to be. If you're looking at something green, it only appears green because the light it's reflecting, the wavelengths it's reflecting, correspond to the colour green. Same if you're looking at something red or something blue. It's only reflecting them because it's reflecting red and blue light. Now, if reflection is that important, we need to know a little bit more about it and how this light actually bounces off and how it behaves when it does. What we would normally do now in class is a little experiment. Obviously we can't do that, so we'll just talk our way through it. So what we would do is we'd pop a mirror down on the table and then we'd draw this line here, which we'll call a normal. And what's really important is that this normal here is drawn at 90 degrees to the mirror. You'll see that come up a lot. That 90 degrees is very important. And then what we do is we'd get the ray boxes out and we'd shine rays of light at the mirror, see how they reflected back. Now hopefully you've already got a pretty good idea how they're going to reflect back. But part of this is knowing how to draw these diagrams and understand them. So immediately there's something missing from this diagram, something that's really important when we're talking about rays of light, and that's little arrows on the rays. We have to draw these arrows to show which direction the light is going in. Now these arrows, they show us that the light is coming in from here, coming in this way and bouncing off the mirror. Light is coming in here, this way, and bouncing off the mirror. You can probably imagine what's going to happen next. I'm going to try and draw it. It's not going to be a very straight line, but what would happen is the light bounces back. Pretend it's a straighter line than that. Okay, and the amount it bounces back matches when it went in. So this angle here, measured from the normal to the ray of light, equals the angle it bounces back at. So if you put in a ray of light really shallow and close to the normal, it's going to come out shallow and close to the normal. If you put in one like this, further away from the normal, it's going to come out further away from the normal. If we then drew another one that was coming in here, like this, making sure we put our little arrows on, it would come out looking like this with the arrows. Okay, that's really important. So let's look at that in a bit of a better drawn diagram than I've just done. So we've got one drawn here, exact same setup, just flipped on its side. We've got the mirror down here, we've got the normal drawn on. Again, we've not shown that it's 90 degrees with a little box here, which we can do. You just need to remember that the normal here will always be at 90 degrees. And we've got things labelled and we've already got the little arrows drawn on. So the normal is always drawn at 90 degrees to the object surface. Notice here I haven't said mirror. Just like with the birds flying and things, reflection doesn't always have to be from mirrors. We're just using that as the example here. The ray of light that hits the mirror, that's this one coming in, we call that the incident ray. Okay, that's the ray of light that's incident on the mirror. The ray of light that's reflected, because we're physicists and we can't come up with very good names, we call that the reflected ray, just to keep things simple and make sure you don't get confused. And we name these angles as well. So here, this angle is called I and this one's called R. I'm sure you can guess. This one called I, we call that the angle of incidence, because it's the angle from the normal to the incident ray. This one here, we call this the angle of reflection, and that's because it's from the normal to the reflected ray. And the really important bit on this slide is that the angle of incidence equals the angle of reflection. Okay? If that's all you remember, that's what you need to focus on. The angle of incidence will always equal the angle of reflection. Now, we want to talk about why we actually do this. In physics, we're trying to think about the uses for the science, okay? Why do we care? What is it used for? Where would we see it in the real world? That brings us on to these things that you can see here. So I mentioned just before that when we're talking about reflection, we're not always talking about mirrors. And these, what you're seeing on the screen now, are some other places that will use reflection. And you'll notice that they're not even flat surfaces, these are what we call curved reflectors. Now, a lot of them, like these, you may never have seen anything like this in real life before, but you've all probably seen something like this on people's roofs or walls for gathering TV signals. These other images are just much bigger versions that we use for looking at space. And they take in light, but not visible light. They take in microwaves or radio waves or other parts of the EM spectrum. And there's two parts to these that we really want to focus on that I want you to remember now because they'll come up in the next slide. So this bit here, the big dish, that's a huge curved reflector. So that's a huge big surface that's going to reflect light. And this bit that you can see here on this one, actually, I'll get the pen out and circle it. This bit that you can see here, and this bit here, and here, and here on the TV one. These are little aerial receivers. And so what happens is the light is going to come in, bounce off that dish, and the light's all going to get focused onto these areas. So let's look at an actual diagram of that happening there. And here we go. We've got a curved reflector down here at the bottom. We've got incoming signals. Now, those signals are part of the EM spectrum, but we're just going to call them signals because it could be radio, could be microwave, okay? We don't know what part of the EM spectrum it is, so we'll just use the word signals. Now, they look like they're coming in at perfect straight lines. And the reason for that is a little bit beyond that 5, but we can still talk about it briefly. It's because the places those signals are coming from are so far away that by the time they get to the reflector, they're basically straight lines parallel to each other. And so then what happens is each of these, as it comes in, there would be a normal drawn at 90 degrees from each of them, which I'm trying to draw, but it's very hard. Okay, so there would be a normal at 90 degrees for each of these, and then what you'll notice is as the light comes in and hits that normal, it's reflected at the same angle as it came in at, but because of this curve shape here, that means when they're all reflected at that same angle, they all get reflected back to this same point. And that focuses the signal, and it makes it really strong with signaling back one place, because all these different signals coming in are all getting reflected to the same bit. And the larger the area of the reflector dish, so the bigger your huge dish is, the more rays it can collect for the reflection. And so then the signal has more energy and is stronger when it's all focused here at this aerial point. Now, we want to actually do a bit of definitions here, like we normally do. So, curved reflectors are attached to receiver aerials to make signals stronger. So, if you have something like this on the side of your house for TV signals, it's because these TV signals are coming from satellites in space. They're very far away, obviously. So by the time the signals get to us, they're not very strong. So what this curved reflector does is it collects all these signals in and focuses them into one place, into one aerial, to make a stronger signal. A curved reflector will collect and reflect many rays to a point called the focus point. And that's where we put the aerial to receive them. So they're all getting focused in there. And then one last bit. We can also use these to send signals out as well as receive them, and they work in very similar ways. So if you had your curved dish like this, and it's got the aerial here on it, and then you had the light coming in like this, and it's getting bounced back there. That's a receiver, that's an aerial, that's receiving signals. But you could have one that was designed to do the opposite. So if you had a dish like this and a little box here, and then what this one would do is, and watch the direction of the arrows, this one would send out signals from this little box to the dish, and then they'd get reflected, so they were all going off in the same direction. Okay, so it can work both ways, but it all depends on which way you've drawn the arrows. And that's why it's really important when we're talking about reflection and refraction, that you always draw these arrows so people don't get confused. Right, that's us sort of finished talking about reflection now. What we're next going to talk about is the idea of refraction. We often discuss and teach reflection and refraction together because they're both to do with how light behaves when it's hitting objects. But when we're thinking about refraction, the light isn't bouncing off this object now. Now the light is passing through the object. Somewhere you see refraction happening all the time is little things you may have seen done like this, maybe in primary school or even at BGE. You might have set up little experiments and talked about why, when you're looking at this, the straw you see here doesn't match up with a straw you see in the water, or the pencil going in here seems to bend in the water. That's refraction, and that all happens because of how light behaves. So the key bit to refraction, and a very important thing you need to remember, and we'll highlight it at the end, is that light changes speed when it moves into a different material. So we should know by now that the speed of light in air is 3 × 10⁸ meters per second. When that light goes into a different material, so for example when it goes into glass, going through a window, it changes speed. Okay? What happens because of this? And we're going to use a little analogy here. So we're going to think of it in other terms first to make sure we're super familiar with it. And so we'll start by thinking of a car and two different surfaces. So we've got some concrete and some mud. So the car starts out on the concrete, it's travelling along at a certain speed, going in a straight line. Then the car reaches the boundary here between the concrete and the mud. So when it reaches this boundary, one of the wheels is now in the mud. And because that wheel is in the mud, it's going to move slower than it would in the concrete. And because this wheel here is moving slower, that makes the car start to turn around. It turns around so much that now both wheels are in the mud. Both wheels are now moving at the same speed, so the car stops turning and it starts moving on. But you see, it's now moving on in a straight line again, but it's travelling slower than it was before. And what's happened to it? It's still going in a straight line, but it's going in a different straight line to what it started out at. It's changed from its original position. And this happened because it's now going more slowly in the second medium. Now this word here, medium, we use that to just describe materials. That's what that means here. So it's going more slowly in the second material. Now, instead of thinking of it like a car, we can use this to help us think about how light behaves. So let's replace the concrete with air. Okay, we've got something just traveling through the air now. And let's replace the mud with glass. So we've still got two different materials. And instead of using a car, we'll use light instead. Okay, and that's what refraction is. Light was traveling through one material, it then went into another material, and it changed speed, and so it changed direction. And we want a diagram of this. So what you'll see is what we've seen before now. We've got a normal here, and what you'll notice hopefully is that that normal is drawn at 90, oh sorry, that's very bad, it's drawn at 90 degrees to the boundary, to the material where it hit. Okay, and what's happened is the light was coming in. We should even actually draw arrows on here. So the light was coming in this direction. It hit this other material, and when it hit that other material, it changed speed. And what that did was it didn't stop the light from going straight, it just moved it a little bit. So it's still going in a straight line, but in a slightly different direction now within the material. So just like before, we call this angle here between the normal and the light, we call that the angle of incidence. And then this angle here between the normal and the light, we call the angle of refraction. It's very important, just like when we were thinking about reflection. These angles here are always measured from the normal to the light. It's never measured from this side to the light or from here to the light. It's always measured from the normal to the light. Now, let's look at a bit of a better diagram so we can actually start thinking about some definitions here. So we've got our two materials, we've got air on this side, then we've got a block of glass here. We've got a normal going through, and I'm just going to pop another normal on there because this is still air on this side. Now, the light comes in. This is our angle of incidence. It has now changed because the light changed speed, going this way. Now, what would happen here? It's changing material again. It's in glass here, and now it's going into air. So its speed is going to change again, but it's going to speed up. It will start going back at its 3 × 10⁸, and so it will change direction again. And so I'll try drawing a nice yellow line for us. And what will actually happen then is it will come out like that. Let's pop our lines on to show the direction. And here we've got new angles of incidence now. So we've got a new normal drawn at 90 degrees. So we've got an angle of incidence here. Let's put an I. And then we've got an angle of refraction there. Let's put an R. And what you'll hopefully notice is that from air to glass, the light bends. Now, this word here, bends. Oh, that's a terrible colour to highlight that in, but that's not letting me undo it. Oh well. The light bends towards the normal. The light hasn't actually bent. It's not curved in any way. We just use that term to say that the direction of it has moved closer to the normal than it was before. Then, if we look at the other side, what's happened now is the light has bent away from the normal when it comes out into the air. Now, the reason for this is a little bit complicated. The key bits at this point anyway for us to remember are that when light goes into glass, it's going to move towards the normal. When it goes from glass back to air, it's going to move away from the normal. But this applies across all materials, and the rule is if light goes into a denser material, it moves towards the normal. Then if it goes into a less dense material, it moves away from the normal. Right. One last bit about refraction. What happens if it's not going in at an angle at all? So if we're looking at this here, you can see that this is our normal. You can just about see it. But the reason you can't see it all is because the light is coming in exactly on the normal. And in that case, it does not change direction. If the light enters or exits an object at 90 degrees to its surface, so on the line of the normal, it won't change direction. It goes in and out in exactly the same straight line as before. But remember, the light angle is always measured from the normal to the light ray. So, definition then from refraction, something that's really key to remember and people often forget. Refraction, the reason it happens is because light travels at different speeds in different materials. It doesn't happen because light bends, that's what refraction is. The reason it happens is because it travels at different speeds. Now, this might cause the light to change direction, okay? But the reason is because of a different speed. Then, finally, let's have a quick think about some applications for refraction, like we did when we were talking about how we use reflectors. So, applications for refraction, there's a pretty big one that's used every day by at least some of you, or some of you'll see used a lot anyway, and that's in glasses. So here, we've got light coming in, then it hit the glass and bends towards the normal, and bends away from the normal a bit, but what it does, it's all focused it into one point here. Or in this one, it's gone in, moved away from the normal because of the shape of it, moved towards the normal because of the shape of it, then moved back away, and it's spread the light out. So we can use that to change the direction of light. That's the biggest use of refractors, to change the direction of it. The reason we might want to do that is for telescopes or microscopes, for glasses, to make sure the light focuses in the right place on your eye. We use it in cameras and lots of other places, okay? So that's where we're going to finish. The key bits to remember are, when you've got reflection, the angle of incidence and the angle of reflection are equal to each other. When you're thinking about refraction, if you're going into a more dense material, you move towards the normal. If you're going into a less dense, you move away. And finally, always draw your normals at 90 degrees and always put arrows on your rays of light. Okay, so again, thank you for listening.